Okay, it seems as attendance is not so good. Let's wait for 1 more minute. Thank you. Okay, let's begin. Yeah, so the attendance is kind of still below 50. Right? So, but let's stop waiting. Okay, let's continue. So last time we talked about the transport layer, right? Mainly the TCP for handshake teardown, and how you can estimate the round trip time, which is useful for determining the timeout. Okay, the timeout RTO, right? RTT is round trip time. RTO is a timeout, the threshold for timeout. Okay, and so today we'll be talking about congestion, right? And the congestion control. Because in the previous set of slides we talked about flow control. Flow control is when the receiver advertise its window, say, hey, I only have that size of window. You don't stand beyond the size of the window of the packets that I can tolerate. So this is a destination-driven flow control. Okay, but there's also the congestion that can happen in the middle of a route where you have maybe a link that is shared by multiple streams, even with different source and destination pairs. But because the link is used by many streams, so you cannot send faster than what is allowed. Okay, otherwise you will have packet drop on that link, and then there's no throughput. So here we are thinking about the congestion where the load on the network is a little bit higher than the link capacity. Okay. So the capacity is often not uniform across networks, right? So for example, if you have fiber optics, it's way faster, right? So in the data center, right? But if you just have like a cellular network, it's a little bit slower, okay? And also, there are multiple flows competing for the bandwidth, right? So, for example, if you are using the cables, right, TV cables to connect to the internet, right? So as we said, the cable actually is shared by all the residents in the building, okay? So you are like competing for the bandwidth, okay? And similarly, in the data center, the hardware is actually shared, right? So if some colleagues are using a lot of bandwidth, and probably you cannot also use a lot of bandwidth because, because all these bandwidths go beyond what the router can forward. Another important thing is that the load is not really uniform, right? So for example, if you get some transmission in the midnight, probably there will be no congestion. But if you do that, let's say, for example, here it's like Game of Thrones, right? So if you have a new episode and then everyone is downloading it, right? So then like at that designated time, then there will be a like congestion happening. Okay. Similarly, if there are some peak hours where people will be using the network. Okay, and congestion can happen during these hours, but in other times maybe there's no congestion. Right. And so why is congestion bad? Right? So this is actually a vicious circle. Okay, because you think about it, right? If you have congestion, which means the router cannot forward your packet so fast, right? There are too many streams coming in. Okay, so the routers have a finite size of buffer, right? So the packets have to be dropped if you go beyond the buffer size. Right? And what happens is that, remember, TCP has a timeout, and so if you drop a lot of packets, that means you will retransmit a lot of packets in the network. Right? This is a vicious cycle. Right? So because if you have a packet dropped and then you will retransmit and still fail and retransmit again. You may have many times more packets thrown into a congested network, right? And it makes things even worse. Right? Once it's get bad, it's really getting bad, worse and worse. Okay, really, it's like to explode. Right? So you don't want that to happen. And so the practical consequences of that is that congestion is that the router queues build up, right? And so which means you have to wait for the packets in front of the queue to clear up, right? Being forwarded to the right outgoing link before you can be sent. Right? So there's obviously a clear delay in latency, right? And there's also wasted bandwidth because now if your packets dropped, right, the previously you forwarded for multiple hops, that's wasted, right, because it doesn't reach the destination and you keep doing retransmission. Right? So this makes the situation really bad. Okay. And there's also a concept of throughput, which is the application level throughput, right? So this application level throughput will be really low, right? Which means even so, let's say you send a lot of data, right, to the destination, right? You actually, physically you send a lot of packets, but it gets dropped in the middle, right, in the route. Okay, so to application, this throughput is not counted. Okay, so your throughput is really low. Right? You don't get your data delivered to the destination. Okay? It seems that the network is stuck and never successfully transmitted. So here we can take a look at like based on queuing theory. Right? So we can consider the throughput of the application, right, and the associated delay, right, curve, like how it looks like. Okay, so we will not talk about the queuing theory details, right? But these are the observations we can achieve when we have this kind of packet switch network, right? And so there are different concepts. Right? Throughput is how much data you can send to the destination. Okay, but it doesn't mean that there's no delay. Right? You can send 1 GB, 1 gigabytes data per second. That's very high throughput. But then the other person may receive it maybe 1 hour later. Then there's very long delay, but always, you can have very high throughput, but also a very long delay. So these are two different criteria. Okay. So in the throughput, we have the need, right? So this is like the need that initially your throughput, right, increase really fast when you have enough load to saturate your network. But when it goes beyond a certain point, which we call the need, the throughput no longer improve if you have more load. Okay? And if you further increase the load, then congestion happens. There's a cliff. Right? There's nothing gets through because your packet got thrown away, right? Dropped by the router, and you retransmit, and then it's thrown away again. So things really get bad. Okay? Suddenly, like a cliff dropping down, right? And accordingly, the delay then becomes, in this case, delay becomes infinity. Right? So because you never get something sensitive, okay? But the delay will gradually build up, So before needs, the delay is really low. Right? When you send, the other side can receive really quickly. But when you go close to the cliff, which means it's almost saturated the network, right? So you will see the delay build up really quickly. Okay? This is the conclusion we talked about in I think probably the first lecture, right? So you should over budget your hardware, okay, your bandwidth. You never utilize almost close to the capacity of the bandwidth. Okay? You should over budget, like only use 20% of the bandwidth. Right? Otherwise, even though throughput is okay, but you will have a very long delay. Okay? And so before the needs, the delay is also low. That throughput is reasonably high. Okay? And when you are going beyond the cliff, what happens is you never get something through. Right? The delay becomes infinity, the throughput becomes zero. Okay? So this is based on the queuing theory, MM1Q, that we have a formula like this, right? So your delay is equal to 1 divided by 1 minus utilization. Okay? So if your utilization is close to 100%, right? You are not over budget, right? You budget about this amount of capacity. Okay? Then your delay will go to 1 divided by 1 minus 1, right? Almost infinity. Okay? The delay will be super. Right? So you do want to just use utilize your bandwidth maybe 20%, so your delay is accepted. Okay, and once you go beyond the cliff, the congestion really happens. Then what happens is that your throughput will go to zero very quickly, and the delay go to infinity. Okay, any questions? let's continue. So the ideal spot is where you don't go beyond the need, but oftentimes it's out of your control, right? Because there are so many different streams. People are sending stuff through the routes, right? So you have no control of the others. So, but we really don't want to go beyond the cliff, right? If you go to the cliff, we should let everyone back off, okay? Like reduce your sending speed. Everyone should reduce sending speed. Okay, this is what the TCP is doing. So here we have two concepts. One is called the congestion control. The second is called congestion avoidance, like we see earlier, right? So in the, when we talk about the, the data link layer, right? So, so you can see that what is congestion control, right? Congestion control. So firstly, congestion avoidance, right? CA is say, hey, you stay at the comfort zone, right? You don't go beyond the need, right? So this is really conservative, right? So congestion control, which is what TCP is doing, is say, hey, you don't go to the red zone, okay, right? The go to the left of the cliff is not good, right? You keep on the left hand side of the cliff, not the right hand side of the cliff. Right? Well, congestion avoidance is keep on the sweet spot, right? On the left of the knee, right? Don't even go beyond the need. Right? So that's the concept. And here in TCP, we are talking about congestion control. Really, you will hit somewhere, you will like have some packet being dropped, okay? And then you back off your bandwidth. Right? So let's revisit what we have for flow control, right? So we have so-called advertised window. If you remember, there's a header field, which is the advertised window, okay? So this is for flow control. Basically, the receiver will tell you, hey, I will have that window size to receive your stream. Don't send packets more than that window to me, right? Pending packets more than the window. Right? You need to acknowledge, and then you send some more. Okay. So the TCP's advertised window solve the congestion? The answer is no, right? So because it just know how fast the receiver can receive. Okay. Congestion is really depending on other people using other streams. Okay, so the answer is really no. The advertised window only protects the receiver. Okay, a sufficiently fast receiver can advertise a very large window, right? But that window is not useful because if you send really fast, right? But the network, the route, right? Some link in the middle really cannot allow such a speed, right? Then actually you still have congestion at that particular link in the route. Okay? So there are potentially concurrent flows. So what's the key point, right? So the key points to avoid congestion is that window size, right? The window size determines the send rate. If you just say the sender's window size is only determined by the receiver, there's no way that you can protect the congestion, right? So window must be adjusted to prevent congestion collapse, which means any link, the bottleneck link in your route, right, should be determined the window size, not any non-bottleneck link, including the receiver. Okay? If your receiver is a bottleneck, of course, the advertised window is good enough. Okay, but if it's some intermediate link in the route, then that link should be determining your window size, okay, not the receiver. So therefore, the congestion control, the goal is to adjust your window to the bottleneck bandwidth, not the last hop. Okay, and it should also adjust to the variations in bandwidth because maybe that link was occupied by somebody sending a very large file. Okay, and then the file is finishing the transfer. Okay, then that stream is teared down. Right, then there's no congestion anymore. Maybe another link will become the bottleneck. So there will be variations. Right, so sometimes you cannot use high bandwidth. Sometimes congestion just is gone, then you can increase your bandwidth, right? So we need to have the TCP protocol be able to increase your bandwidth when there's less congestion and then back off when you detect more congestion, right? So this is the variation. So it should be a dynamic process. Okay. Thirdly, it should be able to share bandwidth between flows, right? So if you have 3 streams going through a particular link, right, each one can use partially the bandwidth of the link. Okay, you should be sharing the links. You should not occupy all the bandwidth of that link. Other people cannot use it. And the ultimate goal is maximize the throughput throughout the link. Right? In the meanwhile, you need to guarantee some fairness. Right? You cannot say, hey, my stream use all the bandwidth of that link. Okay, other people cannot use it. Also, we want to maximize the throughput of all the users, all the streams. So the general approach, right? There are several ways you can do that. Okay, the first thing you can do is you do nothing, right? You just send packets indiscriminately, right? So that will cause many packets to drop, right? And this will have the collapse. Okay, congestion happens. Okay, then you have something that never sends through. Right? A better solution, but could be a little bit complicated. We will see some solution in the next set of slides. Okay, the router well, can help the transport layer to reserve some bandwidth, right? But this is very complicated, right? We call it reservations. Okay, we can pre-arrange bandwidth allocations for flows, right? Say, hey, this flow use how much of the link bandwidth, that use how much of the link bandwidth, right? But this requires, negotiation before you send packets, right? And if your router doesn't support that, because we are in the transport layer, right? So your routers are in the network layer. If you don't have the hardware support, then you cannot guarantee reservation will work. Right? So especially for TCP, we cannot assume like an IP layer is, there's like a router support for that, okay? So the other solution is called a dynamic adjustment, right? We can probe, right? We can estimate the level of congestion because you keep send stuff and you get some acknowledgement or like a timeout, right? So these signals can tell you to estimate how likely the route is congestion, okay? And you can speed up when the estimate congestion level is low, right? But if you find, hey, there's a lot of congestion, you should slow down, okay? Slow down your sending speed. So this is, quite messy, right? So because of the dynamics of the congestion dynamics. So it requires distributed coordination. And so that's what TCP, congestion control, is doing, okay? So how to do that, right? So firstly, if you remember, the sender maintains a window, right? The window is determining how fast you can send, right? So if you have these packets acknowledged, right? So if you have these packets acknowledged, then they are moving out of the window, right? Because they have been fully committed, right? So you don't need to keep them for retransmission. Now the window, like your application right to here, then these data are yet to be sent, okay, not successfully delivered, okay, these data here, okay, right. But you should maintain a window, right? So you say, hey, now even though you can send so many data, you can send it in full speed, but no, I should have a window, right? I can only send those data if you have a window size here, right? Unless you acknowledge more packets, right? Then you can move this amount forward, right? So this window really controls how fast the sender can send to avoid congestion, okay? So this window limits how much data is being transmitted, right? The other data, you cannot even send it, right? Although the application say, hey, send it, right? So let's go beyond my window range. These packets should wait. These segments should wait. So how do we handle this, right? Previously, we have a advertised window, which is advertised in the header, right? The response header, okay? The TCP transmit and then it will respond to you, okay? Acknowledgement will have this advertised window. But now we have another window that is a so-called congestion window, C window, right? Congestion window, okay? And then we should take the minimum of both, right? If there's no congestion link, the bottleneck really on the receiver side, then this will work, right? If there's receiver window is too large, right? There's some link, bottleneck link is even smaller, then this means we'll control that to be the C window, okay? The C window is actually what we will be estimating, right? So the rest of the different kind of protocols variants in TCP is really adjusting the C window, which will limit, right? If your C window, congestion window is even smaller than the advertised window, you will use a C window as a window instead of that, okay? And so there's also a concept of effect window size, right? So you think about it, right? So this is the last byte send, right? You have sent those segments, but you have not acknowledged that, right? So you only acknowledge those, right? Maybe the next one is not acknowledged. So these are in transit, we call them in transit, right? So they are still sending, okay? And then hey, this window size, right? You can at most send packets to here. right? So you can continue to send those, but you cannot send beyond here, right? Because these are not committed yet, these are not acknowledged, and you can continue to send. But when you send to here, you should stop until some acknowledgement move forward, the frontier move forward. Then you can continue to send these packets, right? So that's the idea. So if you look at here, this is what is in transit but not acknowledged, right? And this is the total window that can be pending for packet. So this is the effective window, right? And you can continue to send these packets, right? Without causing congestion. Any question about this concept here before we move on? Okay, let's continue. So there are two basic components in TCP. Right? The first is can detect congestion. Right? So when you increase the bandwidth, how do you know that congestion is happening, right? So the first thing we need to do is to detect congestion, right? The packet dropping is a reliable signal of congestion is happening, right? Because when the queue becomes full for a router, then you will have a packet dropped, okay? And so TCP actually, the basic version relies heavily on the packet drop. Right? Packet drop is a signal that you kind of reach the reach the capacity window that you can allow. Right? Going beyond that, you will have packet drop. Okay? That's the ceiling of the bandwidth you reach. Of course, you can also use the delay-based method because, for example, you send a packet, you will get the acknowledgement. Right? If you remember our RTT round trip time estimation algorithm, right? We can estimate the delay, right? But delay is actually risky. Okay, it's hard. Sometimes there's some fluctuations. The most reliable signal is really if you really find, hey, I have a timeout, right? The packet dropped. Okay, then that's a pretty safe signal saying that hey, now congestion is happening with this speed, this window size. Okay. So how do you detect packet drops? So there are several ways. One is timeout. Right? So if you find a timeout, like if you remember, we have twice the RTT time, right? If you, after twice the round trip time, you still didn't receive a acknowledgement, you think that packet probably dropped in the middle, right? The receiver didn't get it. So the timeout is one signal of packet drop, which means the current window is too large. Okay, we should back up. Another example is so-called separate duplicate ACK network, right? So this is happening because, for example, you have packet 4. But let's say packet 4 send. Okay, there's an acknowledgement received. Okay, for acknowledgement. Okay, let's send 5. Unfortunately, there's a packet drop here. Okay, then you can continue to send 6, 7, 8. Okay, you can send. Assume that they are successful. They get 3 acknowledgement back, right? But because 5 is lost, we will see 4 again, because this acknowledger only acknowledges whatever is before this is received. Right? 5 is not received, you cannot move the window forward. Okay, so you see so-called 3 duplicate ACKs. Okay, if you see duplicate ACKs multiple times, then it's a signal that congestion is happening. Right, so this is another signal congestion. Right, because you lose a packet. Right, if you don't lose a packet, you will not see the same. Right, it will move forward. Okay. So that's a variant that we'll also consider this. So packet drop is for wireless networks, we need some additional methods because the wireless channel, is you can have packet drop because of interference very easily. Right, it's not a wide connection. Right, so we need some other method like delay-based methods to detect the signal. Right, so packet drop is no longer a safe choice. We need some TCP variant that is more delay-based. Okay. So how do we adjust the sending rate, right, according to packet loss? Right? This is the second component of TCP, congestion control. Okay. Firstly, you need to modify the window, right? So if your congestion window, you find a packet drop, right, then you should back off, like cut your window size by half, or even reduce to 1 or 0, right? Starting to pile up again, to probe again. Okay. So you should reduce the window when you find a packet drop, and then if everyone reduce the window, right, congestion will not happen because you think about it. As soon as you detect congestion, everyone is backing up. Okay, then that's right when the congestion happens, everyone will back up. Right, then you immediately drop to where there's no congestion. Right, and then you should increase your bandwidth and probe again, right, I can increase a smaller window again and then respond to the condition. So let me see. So I think we should take attendance for now, okay, because usually some students will join like after 3. So let's take a quick attendance. Nasaj? Nasaj, are here? If I pronounce wrongly, just let me know. Okay. Nasaj, Bahat? No. Ryan?
I'm here.
Okay. Michael?
Here.
Okay.
Sorry, so you're just talking about
What? Sorry, I didn't. Someone just spoke, but I didn't quite get it. Okay. So we are taking attendance. Okay. Cass? Cass, I hear. Okay. See you in the chat. Okay. Rachel? Rachel, I hear. Rachel?
Yes, I'm here.
Okay.
Hello, can you hear me?
Got it. Got you. Yeah. Jackson? Jackson, I hear. Jackson, hi. No. Jalin?
I'm here.
Jalin?
I'm here.
Francis? Francis? Francis Lowenstein? No? Yeah, the attendance today is extremely low. So it's possible. Okay. Andrew? Andrew? Okay, I see you. Francis, okay. Francis is here, right? Trina? Okay, so once Francis joins, just tell her to contact me. Okay, so I will fix this. Okay, just maybe type in the chat. I will fix it. Okay. Sarah Newton.
I'm here.
Okay. Daniel. 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 No. Baraj. Baraj. Baraj Paddle. No. Carlos?
Here.
Jack?
Present.
Okay. What? What's
here.
Okay. Karima, you are not called. Okay. So
Dr. Yan, I'm here. I'm sorry.
who is here?
Francis Lowenstein.
Okay. Let's take a second list. Matthew?
I'm here.
Ebony?
Here.
Arohan?
Yes, sir.
Kashay?
I'm here.
Anissa? Anissa? Are you here?
I'm here.
Okay. Swetha, are you here? Swetha?
Yes, I'm here.
Oh, okay. All right. Okay. Thank you. So that's all for the attendance today. Okay, let me continue. Yeah, the attendance today is somehow very poor. I'm not sure why. So if you know the reason, just let me know. Thank you. So the next is a rate adjustment. Okay. So so TCP, right? So TCP is acknowledgement clock, which means that there's a timeout. If you by twice the round trip time, you didn't receive a acknowledgement. You think the packet is lost. Okay. So the congestion is.
Did you call me? I was here. I forgot to say here.
Who is speaking?
Viraj Patel.
I think so. Let me go to the.
I was stuck on mute the whole time. My bad.
Okay, I will fix that. Let me see. I lose my mouse somehow. All right, let's continue. So congestion also means a delay, right? Because we need to wait for twice the round trip time to know there's a congestion, right? So there's a long waiting time before acknowledgement, right? And there's no congestion also means no delay because acknowledgement arrives quickly, right? There's no timeout. Right? So the basic algorithm for rate adjustment is that upon receiving acknowledgement, you should increase the window, right? Because if you get some packets acknowledged, which means the sending speed is okay, right? You can increase the sending speed. So data would delivered, perhaps we can send it faster, right? So, the congestion window can grow proportional to the round trip time, okay? But if your round trip time is fast, right, short, then you can grow faster. If your round trip time is long, probably there's some congestion happening, right? There's some packet build up in the queue, you should not increase that fast, okay? Until a point where you increase the window size and suddenly there's a packet loss, right? There's an acknowledgement that is missing. Right? Then there's a data loss, there must be congestion happening. Right? You are confirmed having a congestion. And like your timeout, right? Then you should decrease the window size. Right? This, keep in mind that TCP is run by everyone. Right? So basically everyone will decrease the window size once they detect the congestion. And then things will get back to normal, and then everyone will increase the window size again, right? To probe the ceiling, where it will go to the congestion. So this is why the TCP protocol can dynamically adjust to the bandwidth, okay? Because you will try again and find a new ceiling. Right? So the question is, what should be the increasing and decreasing function to use in these two operations? Right? If you get acknowledgement, you should increase the window, right? But if you have a packet loss, like timeout, you should decrease the window, right? So how to increase? How much do you increase? And how much do you decrease? Right? So this is the question that we are answering here, right? So let's consider a simplified case where you will have basically, you have a link. Okay, so here we are thinking about a particular link, right? And you have two streams to send over the link. Okay, like this is one stream sending through this link, another stream sending through also this link. Okay, right? So we call this flow one. This is flow one, and we call another one is flow two, right? And let's say this link, the capacity that you can send as a throughput at most is C. Ideally, everyone is using 2C, okay? Right, so this is the ideal case. So let's think about a case, right? So this is a particular point where flow one, the coordinate flow one is smaller. Right? So if you look at this point, flow one, maybe this is maybe 5C, okay? But this one is larger, okay? Maybe this is 5 by 4C, okay? 5 by 3C. And you can see, so basically this guy is just using 20% of the capacity, right? This is using 60% capacity, then you are here, okay? And this is the line where, throughput 1 plus throughput 2 is exactly capacity, okay? This is the capacity, x plus y equal to c, okay? This is x plus y, which means the capacity exactly equal to c, okay? This point is below c, right? This is 80% of c, okay? And so, if you look at a particular point here, this point is saying, hey, this point here is saying, hey, if you look at flow 1 throughput is 0, right? So this guy is using 0, okay? While if you look at throughput 2, this coordinate is C, right? This guy is C. So this is unfair, but it's maximum throughput, okay? Because any point here is maximum throughput, okay? If you are here, then this is the other case, right? So the flow 1 is using all the capacity, and flow 2 is not using any capacity, right? So there's a fairness problem. Right. So if you are on the left-hand side, the downwards triangle area, that means you're not fully utilizing the capacity, okay? But if you are on the orange triangle, right, above the line, that means you go beyond your capacity. X plus Y is larger than C, okay? Then congestion happens, okay? You will have packet loss. And ideally, you want to have this point in the middle, which means, everyone is using C by 2. Right? This is the ideal case, right? So this is the toy example we are having. Perfect fairness, everyone using half of the capacity of the link. So let's think about several functions that we can use, right, to increase and decrease the bandwidth. Okay. So first is when you increase bandwidth, right? If you remember, increase means your congestion is not happening. Okay. If there's no congestion, then you can increase, which means you're on below this line, right? If you increase multiplicatively, right? So if I say, hey, I'm okay, right? So this bandwidth okay, I double my bandwidth. I go to here, right? And similarly, this bandwidth is okay, I double my bandwidth. This is each time 2, you will reach here. Right? This is going to be larger than 45 degrees. Right? 45 degrees, you increase by 1 each time. Okay. If you increase suddenly, it will jump. Slope is really high. On the other hand, if you decrease, everyone decrease by 1. Right? If you decrease each coordinate by 1, then this is called decrease linearly. But increase, it's faster. Slope is higher. Okay. If you do something like this, what will happen? Right. Initially, let's say you are here and the congestion happens because it's above the line. Then what you will do, it will decrease linearly, slowly decrease, right? Additive decrease. Right? So you -1 decrease to here, okay, along the 45 degrees. But then you find, hey, now I can probe, I can send fast. Then you increase. Right? You will increase. Right? It's like 3 times. Right? It's like along each axis. Okay. And then you increase larger than 45 degrees. Right? And then you find the congestion happening after you jump into there. You linearly decrease along the 45 degrees. And you keep doing this, right? So you can see that it's pushing away from the green line, which is the fair. Okay, so this is not good, not stable. So we cannot use this scheme. The second scheme is called additive increase, additive decrease, which means, hey, if congestion happens, you allow the 45 degree line going back, and then you find, hey, now there's no congestion. Everyone increase linearly, right? Each time by 1 on both sides, and then you go back to this point. When you congestion, then you come back. This is really stable. Okay, it will not have fairness problem. If you are not fair initially, it will not get worse. It also doesn't get better. Right? So it's like above this line and keep on this. Okay, so it does not convert. It does not bring you closer to the green line. So another option is called multiplicative increase, multiplicative decrease. Right, it's larger than 45 degrees. Right, you suddenly like congestion happens. You suddenly cut your bandwidth by half along each axis. Right? So along each axis. And then you find, hey, there's no problem. I jump twice again. Right? So this is stable. Right? You're jumping around this line. But again, it does not get you closer to the green line. Okay? You are stably being unfair. Right? So the true solution that's used by TCP, the best way is called the additive increase and the multiplicative decrease. So what it means is this. Right? So you want to converge to stable and file. Right, so what you do is this. Right? You will, if you find congestion, right? For example, you find you are sending with this bandwidth on flow 1, this bandwidth on flow 2. You find, hey, there's congestion. So what I do is I cut my bandwidth immediately by half. Okay, it's a half of this, and this is half of that. Okay, but I decrease more than 45 degrees. Okay, but after that, there's no congestion, right? And then I slowly increase. Everyone increase by 1 each time, right? And then slowly along 45 degrees, you go slowly increase until a point where you go beyond this line and the packet loss into time. Right? And then you immediately do multiple decrease again. I cut the bandwidth by half each year, and then you do this. But you can see this has a desirable feature that, you know, you, no matter where you initially are, how unfair you are from the green line, you will get close to it. This is another example on the other side, right? It's unfair, but in the other way, right? Which means if flow 1 is more favorable, here flow 2 is more favorable. But anyway, as time goes by, they will adjust their bandwidth to a point where everyone's using the same share of the capacity of flow, right? So that's why we are using this additive increase, multiple decrease solution. Okay. So any question about these animations to give you the idea why we are using additive increase and multiple decrease? Okay, if there's no question, then let's continue, right? So to implement this congestion control, we need 3 variables, right? The first is the congestion window. The second is the advertised window, right? So this is a receiver window. This is a congestion window that we probe, right? And using this bandwidth increase and the decrease, okay? And remember, our actual window size is the minimum of these 2, right? The smaller windows. And we will also have a so-called SS threshold, right? So this is the threshold size used to update the window. Okay? We will see what it is. And as we described, the sending window is really the smaller among the receiver window, advertised window, and the congestion window we probe. Okay. So there are 2 phases in congestion control. Right? Remember, we have a surge threshold here, SS threshold. Right? There are 2 stages. The first stage is called slow start, right? Which means if your window is initially very small, because you probably begin from window size 1 packet at a time, right? Then you should do slow start. Okay, probe for the bottleneck. Yeah. When we are in slow start phase, actually we are not slow start, we are starting really quickly. Okay, we'll see that shortly. Okay. And then we have the congestion avoidance, which means if I go beyond this threshold, then I should play safe. I use this additive increase and multiple decrease solution we talked about. But initially, if you do that, right, you will have very slow increase. Right? What you want is really, you want to do exponential increase. Although it's called slow start, it's really faster. But go beyond a certain point, you start to slowly probe, right? But initially, you know, if you are 1, then 2, 4, 8, you can increase quickly initially. Okay, you don't want to increase 1, 2, 3, 4, 5, 6. Right? That will really make the reaction really slow. Okay. So the first phase is called slow start, where we want to reach the knee quickly. Right? If you remember, this knee is where it's a safe zone. Okay. So upon start or restart connection, your initial window size is 1. That means each time you only allow 1 pending packet segment, right? And until it's acknowledged, you can send the next one. Okay. And the threshold initially is set to the advertised window, right? The receiver, the maximum allowed size on the receiver side. Okay. And then what you do is each time, you know, a segment acknowledged, you will increase the window size by 1. Okay? Whenever you receive an acknowledgement, you increase the window size by 1. Right? So why this increase just by 1 for acknowledgement? Right? So it doesn't seem really fast, right? But actually, it's really fast. Okay, let's take a look at why. So this continues. This thing continues until either the SS threshold is reached, which means you reach the knee, or estimated point of knee. Okay, or the packet loss, which means you reach the cliff. Okay, then this should stop. Because this increases really fast. Let's take a look at why. Okay, slow start is not actually slow. It's increase the window size exponentially, even though you think it's just an increase 1 for each node. It's exponential increase. Right? So let's take a look at why this is exponential. Right? It's like doubling each time. Right? So here's the animation. Initially, your window size is 1. So what it will happen is that it will cause, you know, just only 1 outgoing pending packets can be there, right? Until it's acknowledged, then you can send another one because the window size is 1. Okay. After acknowledgement, right? So we know that, hey, now we have a gray acknowledgement. I should increase it to 2. What will happen is now you will send 2 packets, right? Because it's clear, right? So then your window can move 2 and 3. Okay. And then you will wait because at most 2 packets can be pending, right? Okay. And then these packets arrive because you will receive 2 acknowledgements, right? 1 for each acknowledgement. Okay. Then you will increase 2 by 2. You get 4. Okay. And next time you will send 4, 5, 6, 7, right? And then you will reach, get 4 acknowledgement, you will get 8. So you can see that each round trip, you actually double your window size. This is exponential. Right? If this goes on, this is really quick, right? So we should stop it some spot that you think it's safe to stop, right? You cannot do this forever. Otherwise, let's say you are quite close to where the throughput will collapse, right? Then you double, right? This you go really too fast. You should, if you go closer to where congestion will happen, you should go slowly, right? One at a time. Right? So this solution obviously cannot hold there. Okay, you should SS threshold is really the knee threshold, okay, not the knee threshold, okay, not the cliff threshold. When you reach the cliff, you should slow down. So what's a congestion avoidance strategy? Right, the congestion avoidance strategy is saying this. Okay, let me give the answer to this. Okay, what if you get an acknowledgement? You should increase the window, but you should not increase the window by 1. It should be increased by 1 divided by the window size. Okay, so this is a much smaller size than 1. Right? And the larger your window is, actually, each time you get acknowledgement, the smaller you increase the window size. Okay, so this scheme is actually the one that is additive increase. Right? Previously, we are multiplicative increase in the slow start phase. Okay, right. So after you reach the SS threshold, right, you should stop doubling your window size each time, each round trip time. Okay, so threshold is a lower bound gas above the location of the knee. Right, going beyond that, you now should be less aggressive. Okay, increase the window slowly in a linear speed. As we said, so this is how you update. The window should add by 1 divided by the window size, current window size. Okay, so the window size, the effect of this is that the window size increased by 1 only if all segments of round trip time is acknowledged. Okay, so let's see what it means. Right. So here's the animation. Right. So for example, if you send by 1, right, and then this is the fast start. Right. So what you do is you fast start till 8, because we think 8 is a need, right? Go beyond 8, we should slowly increase the bandwidth. If you double it to 16, immediately you have very bad congestion. Everyone is doubling. Right? So you assume that we can quickly increase to 8, then we should linearly increase. Okay. So if that happens after you reach window size 8, okay. Now next, if I get an acknowledgement, okay, what I would do, remember here it's a 4, right? Plus these 4, I reach 8. When I reach 8, whenever I get this, I only increase 1 by 8 because my window size is 8. Okay? 1 by 8, 1 by 8. Okay? If I do this, right, then I will only increase 1 after a round trip time. But this round, I only increase 1 to 9. Next time when I send, in the next round trip time, I only send 9 instead of 8. Right? And this time, each acknowledgement will increase by 1 by 9. Right? Then your window will go to 10. Okay? So you can see that only by adjusting your window size to be this number, okay, 1 by the current window size, where you later, after SS threshold is good, you will probe in a less aggressive manner, linearly, 1 and 1 each time. Okay? Right. So this is called the second stage. We call it congestion avoidance. Okay? Right. This is slow start, which is very quick. Okay? And then once we go beyond the knee, we really slow down, okay? Until we get the ceiling where we have packaging. Okay, so that's all for today because of the time. Okay, any questions? If not, we will continue the rest of the TCP protocol on Friday. Okay, and I will upload this video to YouTube. Okay, thank you. Have a good one. I don't see any questions, so I will disconnect and feel free to send me email if you have any questions.